15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on Space Nuts, and great to have your company. I'm your host, Andrew Dunkley. And on today's program, we're going to be looking at how star-making galaxies cause galactic pollution on a massive scale. So it's not just people, it's the whole galaxy that does it. And a lot of galaxies apparently are very, very messy. They don't pick up after themselves. They leave socks on the floor. It's not a pretty place. And stars that are eating their own planets. And it's possible that as a consequence of this, the number of Earth-like planets out there might actually be less than we think. Plus some audience questions. David in Texas has got a black hole question. Surprise, surprise that people would ask black hole questions. And Martin in Wollongong is following up on something we spoke about recently, Asteroid 2021 PH27. With a few thoughts there. So we will get into all of that today on Space Nuts. And joining me, as always, is his good self, the Professor, Fred Watson. Hello, Fred.
Hi, Andrew. How are you doing?
I am well. How are you?
Very well, thank you. Survived the move okay, and new surroundings.
You're in your brand new house, which is really old. It is. Still got suits of armour in the corridors and.
Yeah. Do you know what the worst thing about it is, Andrew?
What's that?
About an old house. There's only one power outlet in each room.
Yes.
Yeah. So there's going to be plug boards everywhere.
Well, the place we're in, which we built 7-8 years ago, has got more PowerPoints than you can poke a stick at.
Yes,
of course,
yes.
The big mistake you make is you try to figure it out on a paper plan as to where you want the PowerPoints and how you're going to lay your furniture out. And when you ultimately move in and put everything down, you go, oh, no. I could have put it on the opposite side of the room. Damn it. It's a bit wild and crazy sometimes. But glad you settled in. I love your view. My goodness.
It's a very nice view out the window, yeah. It's that's what sold the place to us. We've got it's halfway up a hillside and we've got this lovely terrace. One day we might even be able to entertain you for dinner, Andrew, or something like that.
One day if we ever get out of lockdown. My word.
But the view beyond it is very...
We've got near 500 cases in town now. So,
wow.
and very sadly this week we had our first death from COVID, which... no one ever thought would happen here, but it did. So very, very sad indeed. Okay, let's get down to business. Where do you want to start? Well, we talk about how star making pollutes the cosmos, how galaxies are filthy, rotten little devils that make a big mess in the universe, the greater universe. I think this is disgusting.
Well, you're complaining to the right person, Andrew. That's if you've got a complaint, just put it in writing. We'll deal with it. Right. In the world of astronomy, it's actually it's a story that, in many ways, is not surprising, but it is. It's nice to see it demonstrated. And the other nice thing about it is that this has got a very strong Australian component. The astronomers, one is now, I think, based in Oxford, but they were part of the ARC Centre of Excellence for All-Sky Astrophysics in 3 dimensions. It's usually called Astro 3D, which is an Australian initiative. And so they have worked using telescopes on the on the mountaintop of Mauna Kea in Hawaii, which is without doubt the finest site for astronomy in the Northern Hemisphere. It's also a very sacred place to the native Hawaiian people, and that's an issue. But the observatories there do sterling work in terms of our understanding of space and the galaxy. They've used the Keck telescopes, or one of the Keck telescopes, which is on that mountaintop. And what they've done is they've looked at the way, first of all, how clouds of gas are pulled into galaxies. And then what comes out at the other end, I suppose that's the best way to describe it.
It's an intergalactic digestive system.
Well, that's exactly what it is. And, and
we all know what happens at the end of that process.
Yes, well, yes, you can draw whatever analogies you like on that,
Space doogies by the,
yes,
by the
probably,
millions.
yes, probably. So what happens is, as you know, the primordial universe, the universe before there were any stars, was mostly composed of hydrogen and helium. They were the normal matter component. Of course, there's dark matter as well, which we don't know enough about. But the raw material for stars is hydrogen. That's the fuel that they burn. And when they are glowing and shining like our sun is, what's going on inside is the manufacture of other elements like helium, like oxygen, carbon. All of these things are produced within stars. So, and then at the end of their lives, the stars, they die in some way. And in a case of a star like the sun, it will have a long life, perhaps 10 to 12 billion years. And when it dies, it will be a fairly gentle process. It will shed its outer layers and the core will collapse into something called a white dwarf. But the bigger stars detonate. They basically go out in a much more spectacular way. They explode. There are a number of different mechanisms causing these supernovae, as we call them. But what the end product is first of all, much heavier elements are produced in the high temperatures of supernova explosions. And the other thing is, because it's an explosion with considerable power, these heavier elements are spread throughout the surrounding space. So they are, in a sense, polluting the space between the stars in that galaxy. Now, what then happens is, of course, new generations are formed. But some of that polluted gas, if I can put it that way, is basically blown back out into intergalactic space, the space between galaxies. Once again, because of the shock waves produced by supernova explosions, and that is essentially the mechanism that delivers the stuff back to the space between galaxies. So we've got one of the lead authors, Deanne Fisher, who's at Swinburne University here in Australia, makes a nice, quotes, the quote is very nicely put. On its way in, the gas is made of hydrogen and helium. By using a new piece of equipment called the Keck Cosmic Web Imager, we were able to confirm that stars made of this fresh gas eventually drive a huge amount of material back out of the system, mainly through supernovas. But this stuff is no longer nice and clean. It contains lots of other elements, including oxygen, carbon, and iron. And so, that's basically what happens. The expulsion of this gas, which is called an outflow, and people who study galaxies look at these outflows in great detail. That's delivering what we're calling polluted gas out into galactic space. But of course, it's because of that pollution that we are here, Andrew, because it's those heavy elements that make planets and eventually a living organism. So we owe a lot to this form of intergalactic pollution.
It also contains traces of COVID, I believe.
Well, yes, there's all kinds of things going on in there that we don't understand.
You talk about this stuff getting blown out by supernovae into the cosmos, into that space between galaxies. On what kind of scale are we talking? We're talking, galaxy-sized clusters of
it's big.
stuff.
That's right. So the outflows are sometimes many, many times bigger than the galaxy itself. Because basically they've been churning this stuff out for a long time. And so, we're talking about hundreds of millions of light years generally in terms of what's going on.
Wow.
Certainly, so I beg your pardon, no, I'll do that calculation again. We're talking about tens of millions of light years, sometimes up to tens of millions of light years. So it's big stuff compared with a galaxy which might be 100,000 light years across.
And what would happen to that stuff once it's ejected and it's out there in the interstellar space?
Yeah, well, it's intergalactic space, the space between galaxies, which is very, very rarefied. And we know from other things that you and I have talked about, actually, that there's lots of electrons, or ions as well, which are atomic nuclei in that intergalactic space. So there is also some of this other material, but it will be very, very dilute. It'll be almost undetectable because it's so dilute. It's only detectable as it's squirting out. When it gets spread out into galactic space, it's a lot harder to detect it.
It thins out and becomes just like a very minuscule oil slick.
Exactly. Yes, that's right. Or yes.
And this is generally caused by stars that die and go supernova.
Yeah. So the thing is driven by the explosions at the end of the lives of massive stars. Now, those massive stars don't last very long. Sometimes 10 million years or so, which is very short on the cosmic timescale. And so that's why you can make this equation, balance the equation of stuff going in, being turned into stars and then into supernovae over a short timescale, and then being pushed out by the shock waves that drive these supernovae. It's a very nice piece of work, actually. It's lovely stuff.
It is fascinating, and of course, the star we're all looking at the moment that is concerning. Well, maybe not concerning, but certainly interesting astronomers in terms of going supernova is Betelgeuse. Is that the one?
That's right. Yes, in the constellation of Orion, it's one that will eventually turn into a supernova. But whether it's tomorrow or in 10,000 years, we don't know.
Or it might have already happened and we haven't seen it yet.
Well, there's that too. Yes,
that's the really fascinating part of astronomy. We're always looking at history. Yeah. Something could have happened, 100 years ago in our lifetimes or in our existence. And we won't see it for, who knows how long because of the time it takes for the light of the event to travel. And I think I want to go back to our star. It's not big enough to go supernova, is it? Ours will go red giant and then, kill us all. There'll be still a sticky end for anybody left on Earth at that time. And we're talking about this process will probably start in 2.5 billion years or something and gradually build up to a crescendo in about 5 billion years. But I think, we might have, who knows what's going to happen to humankind? Will we just die off, or will we escape the solar system altogether and send the goo through space, as we discussed a couple of weeks ago? Here's an interesting question. I keep thinking of questions. I don't know what's going on today. I'm acting like a journalist. Let's just say humans are still around when the process of our sun going, red giant starts to happen, and we have to leave the planet. And we have the capacity to move to Mars and live there. How much time would that buy us?
Yeah, probably on a human scale, it might buy us quite a lot of time. Yeah. You might be talking about a few million years. But it's going to catch up with you eventually because Mars is doomed as well when the sun turns into a red giant. We do know that planets can survive that process because there are certainly examples of planets in orbit around white dwarf stars, which are the final end product of this. Planets can survive without being completely melted, but it's not going to be good for any biospheres on those planets.
So if we time it right, we move to Mars and then we move again, maybe out onto one of the moons of Jupiter or Saturn and just, sit it out. And then when it shrinks back to white dwarf, we move to Mercury.
Maybe that's right. That's the trick. If you could do that, look, that's very good planning.
I'm a thinker.
You're a thinker, all right. You should be on the Intergalactic Council, Andrew. And
you never know. And I can watch it all from the restaurant at the end of the universe.
That's right, exactly.
All right. Some fascinating discovery in terms of how we junk up the cosmos just by being. Full stop. Yes, it's just the process that it just proves that a galaxy is just like a giant toilet system. What goes in and what comes out, just a big mess. This is Space Nuts. You're with Andrew Dunkley and Fred Watson. Let's take a little break from the show to tell you about our sponsor, NordVPN. Now, these days, cybersecurity is all important to just about anybody. It doesn't matter where you are or what you're doing, you could be exposed to cyber criminals. And let's face it, it is big business these days trying to get into your personal details, to hack your bank accounts, whatever it is they're trying to do. Well, as a Space Nuts listener, we've got a special deal for you to join NordVPN. And the deal is 2 years, a 2-year plan, and you can add on 4 months for free, which is a fantastic deal. Now, what are the advantages? Well, if you look at the endorsements that NordVPN has received, I think you'll be pretty impressed. They've got the backing of some big name organisations, including the BBC, Forbes, TechX, BuzzFeed, the Huffington Post, Wired, all prestigious organisations and websites. And it makes your online data unreadable. That's the bottom line. And you can use it all the time. You don't have to just use it when you want to use it. You can have it set up so that it switches on when your computer or your iPad or your iPhone is operating, and away you go. And it will protect you. It'll just make everything you're doing unreadable. And especially if you're using a device in a public setting where there's a public Wi-Fi service, you don't really want to get caught up in that situation, because that's where the hackers really do their stuff. So you can shield your browsing from criminals and from surveillance. And of course, a lot of governments these days like to know what you're doing. You probably don't like them to know what you're doing some of the time. So you can get security there, and it will secure all your devices. You can secure up to 6 devices with a single NordVPN account, including your smart TV. And it also enables you to access the global internet. So if you want to do something through a server overseas and you get geo-blocked, you just log into a server in that country and you can get in there, whether it's a TV service or whatever. It's quick to connect. It's very reliable, high-tech encryption. It's even got things like a kill switch, and it is the fastest VPN on the planet. And as I mentioned to you last week, I've actually logged into my NordVPN and found that I've had download speeds faster than my open internet service, the one I pay for, which I find incredible. So if you're looking for online freedom and security, NordVPN is definitely the way to go. Now, as a Space Nuts listener, you have the opportunity to take advantage of this offer, 2 years plus 4 months for free, simply by logging on to nordvpn.com/spacenuts. It's a special URL, and consider this: the 2-year plan comes with a big discount and works out at just $3.18 a month. You know, it's you pay more than that for coffee. So $89 for the 2 years instead of $334.50 plus 4 months free. So the 2-year plan is a pretty good deal in its own right, with a bonus 4 months added on. Only available to Space Nuts listeners. nordvpn.com/spacenuts to take advantage of this wonderful deal from NordVPN, our sponsor. And now back to the show.
3, 2, 1.
Space Nuts.
Now, Fred, our next story is focusing on something as messy as what we were previously talking about, but on a smaller scale. This is stars that tend to eat their planets. It's like tigers eating their children, by the sound of things.
It's very like that, yes, only even messier probably in terms of certainly what would happen to the planets that get eaten. It's a really interesting story with all kinds of ramifications. And once again, it plays into the fortunate position that we are in on our own planet, because it may be that we are relatively unusual.
We already knew that.
We knew that, yes. This is one of the arguments, that feeds into, for example, the Drake equation, how stable are solar systems, how long do planets last. And we live in a solar system which is extremely well behaved, if I can put it that way, in terms of the planetary motions. The planets orbit in mostly almost perfectly circular orbits. They're very stable. We do believe that in the early history of the solar system, planets migrated inwards and outwards to some extent, and maybe Uranus and Neptune swapped positions. That's something else that's a possibility. But the general picture over the last few billion years, and remember the solar system's about 4.57 billion years old, over the last few billion years, there's been a high degree of stability. And that's a great thing for living organisms to evolve. As life, for life to evolve to a high level of capability, you want it to be in a totally stable environment. And as we've mentioned many times before, one of the contributors to that might be the moon. The fact that the moon is a relatively large body compared with the size of the Earth. It's 1/80th of the mass of the Earth, which is big compared with the other moons of the solar system in relation to their parent planets. So the moon has had a stabilizing effect on the Earth's rotation, made for a stable climate. And here we are as a result of that, highly evolved creatures from whatever origins we had.
Yep.
But it's possible that all solar systems aren't like that. And there is certainly among the sun-like stars in our neighborhood of the galaxy, there are some that would be expected to have fairly chaotic orbits. Now, it's not an easy thing to detect. You can't just say, it looks as though that planet, that Jupiter-like planet, might have migrated within the last few million years. It's not the sort of thing that you can measure because we observe these solar systems on timescales of years, not timescales of millions of years. But there is, when you look at the theory behind the way solar systems work, there is the definite possibility that chaotic orbits can have quite catastrophic consequences for planets. If you've got, planets whose orbits migrate inwards and outwards fairly rapidly, they will interact gravitationally with other planets in that system and could either kick them out of the solar system altogether, and it's possible that happened in the early days of the solar system, or sort of kick them inwards so that they are overwhelmed by the gravitational pull of their parent star and they get gobbled up by it. Essentially, they fall into the parent star, probably by spiraling inwards over many, perhaps millions of years, but eventually becoming part of the parent star itself. Now, that sort of thing is very hard to observe unless you're clever, like these astronomers who carried out this work. Once again, there's a strong Australian flavour in this, with scientists from Monash University, actually now in Italy, but doing some work on this at Monash here in Australia. What they've done is they've taken an alternative approach, which is to look at the chemical composition of the star itself. Because, and this is in a sense, it has echoes of the last story we did. Yeah. If you look at the chemical composition of the star itself, you can see whether it has been polluted by elements that you would find in its planets. In other words, it changes those elements will be in the parent star anyway, but in different proportions if it hadn't eaten up a planet. So by gobbling up a planet, you change the constituents of the atmosphere of the star. And that allows you to measure that, because we can do that with the spectroscopic technique, where you break the light into this rainbow of colours and it reveals the barcode of information that tells us exactly what constituents are in the atmosphere of a star. If it's polluted by the debris of a planet, it will show up. And that's the really interesting aspect of this paper, because what these scientists have done is to look at there's another ingredient to the story, actually, which I've not mentioned, and that is that if you to give you a baseline as to what your star, the chemical composition of your star would be before it ate up the planet. To give you a baseline, what you want to do is to find stars, pairs of stars in orbit around one another, things that we call binary stars, which is actually up to half the stars in our galaxy are binaries. They're two stars in orbit around one another. We're quite unusual in that we're not, or at least 50-50 we're unusual we're not. So now the thing about binary stars is that they're made at the same time and from the same gas cloud. So they are expected to have the same mix of chemical elements.
Oh, I see where you're going.
Yeah. So if one of them's gobbled up a planet, then it will show a difference from its partner. That's the crucial point of this work. And so what these scientists...
As you love to say, Fred, that's the smoking gun.
Well, yes, and it's probably pretty smoky if you've gobbled up a planet.
Yeah,
yeah. So what the scientists have done is they've looked at more than 100 binary systems with sun-like stars in them, and essentially looked at the spectrum of light of each of the binaries. And what they've been able to do is find how many of those stars, one star in a pair, contains more planetary material than the other one, than the companion. And the fact is that the stars have differences. What they found, and I might quote from this. This has been written up by one of the authors, Lorenzo Spina, in a Conversation article, and he's put it very nicely. What he says is there are three ingredients that tell you unambiguously that the chemical differences between the pair of stars were caused by eating planets. And the first is that the stars with a thinner outer layer have a higher probability of being richer in iron than their companion. This is consistent with planet eating, as when a planetary material is diluted in a thinner outer layer, it makes a bigger change to the chemical composition. Our cat's just done something a bit unusual. I'm not quite sure what it is, which is why there was a clatter there. I think he's knocked. I think all he's done is rolled over and knocked the TV remote control off where the table that he's lying on.
He's probably investigating his new digs.
He's done that. Yeah, absolutely. So I'm sorry for that digression. So thinner outer layer is one ingredient with its richness in iron. Secondly, stars richer in iron and other rocky planet elements also contain more lithium than their companions. Lithium is quickly destroyed in stars while it is conserved in planets. So an anomalously high level of lithium in a star must have arrived after the star formed, which fits in with the idea that the lithium was carried by a planet until it was eaten by the star. And then the third ingredient is stars containing more iron than their companion also contain more than similar stars in the galaxy. However, the same stars have standard abundances of carbon, which is a volatile element and for that reason is not carried by rocks. Therefore, these stars have been chemically enriched by rocks from planets or planetary material. So there you go. Those are the three things. And the bottom line is that between 20 and 35% of sun-like stars eat their own planets, with the most likely figure being 27%. So, a quarter of sun-like stars actually consume planets. They have planets that are in such unstable orbits that they dive into the star.
I'm feeling lucky. I think I should buy a lottery ticket.
Yeah, you should.
Yeah. I suppose that also means that in our search for Earth-like planets, we are going to be able to dismiss 27% of scenarios because it may not be possible for these planets to exist or exist long term.
Over long periods, that's right.
Yeah, and that's one of the things in the search for livable planets is that they're looking for things to dismiss so they can narrow their focus. We talked about that some time ago. Yeah. This may well add another element to that, it will. That approach.
Exactly, it will.
It's also a bit disappointing in that that means there are fewer Earth-like planet potentials out there because of this strange orbital situation and these hungry you can look at it from both angles, I suppose. Of course, something else you and I spoke about not so long ago is the fact that our star used to have a binary. It used to be a binary,
Probably.
didn't it?
Probably.
We think?
Yeah, we think so. Because most stars seem to be formed in binary systems. So something happened, probably gravitational attraction with other stars within the same cloud of gas that the sun formed might have kicked the sibling off somewhere in the wilds of the universe, is a star which was our twin companion.
Yeah, I wonder, would it be ever possible to find it? That would be a big ask.
People are certainly looking. So what you look for is what we've just been talking about. You look for a star with an identical chemical composition to the sun, and then you try and look at its motion and sort of wind that back to see if it was ever in the same neck of the woods as the sun was. That's the way you do it.
How far apart is too far to dismiss stars being binary? I mean, what's the limit on a binary system in terms of distance between the stars?
It's measured in light years, actually.
Right.
So rather millions or trillions of kilometres. And what you're looking for when you find binary stars is you're looking for stars with, first of all, this identical chemical components, but also with sort of matching velocities, so that you know that it's not just two stars that happen to be close together, that are whizzing past one another, that they've got velocities that are within cooey of each other. Yeah.
Interestingly, though, Fred, and we've said it before, the more we start to learn about our situation, our solar system, our sun, and compare it to what's going on out there, the more we discover in terms of exoplanets and solar systems and other galaxies, the more rare we seem to be.
Yes, that's right. Indeed.
Which adds more weight to the "we are very much alone" argument.
Yeah. Certainly, it certainly contributes to understanding the Fermi paradox, which is where are they all?
Yeah.
If we're very unusual, they're out there.
Maybe so. Time will tell, but maybe not enough time for us. Who knows?
Yeah.
This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, I'd like to say thank you to our patrons who continually support the Space Nuts podcast, and we really appreciate that you're putting a few dollars in the tin can. I've got to tell you a funny story. I got a call from a fellow who is in town here who I said that the way we support the program is that I have a tin can at the front of my house and anyone passing by should drop some money in it. He rang me up to find out where the tin can was. So I was, that's lovely. And I haven't gotten back to him, which I really need to do. But we appreciate your support as patrons and a few patrons to recognise. So, and our episodes are brought to you with the support of patrons. And this week we shout out to Satakupa Johnson, Brian Peterson and John Harvey, who are all significant contributors to the Space Nuts podcast. So thank you for being patrons. If you'd like to look into becoming a patron, you can do that by visiting our website, spacenutspodcast.com or spacenuts.io. And all the information you need to know about becoming a patron is there. And while you're there, check out the shop and all the other stuff that's going on, the newsletters, everything we do is on the website. Okay, Fred, let's see if we can solve some curios from people who have questions for us. And our first question comes from David in Texas.
Hey, Andrew, Fred, and Gregory. My name is David from San Marcos, Texas. I got a question for you about black holes. Theoretically, black holes have infinite mass, and space-time is laid out in a way to where gravity dips space and time. So, if black holes have infinite mass, shouldn't they be able to tear space and time at the singularity point? And if they can move, how is it that they don't leave a trail of shredded space-time behind them? Don't quite understand it. If you could please elaborate on it for me, I appreciate it. Thank you, guys.
Thank you, David. And I think that was your seatbelt alarm I could hear going there. Yeah. Infinite mass, is that not?
No, in fact, they don't have infinite mass, but they do have infinite density. So the
It's
mass,
always confusing. It's always confusing because
it is.
Yeah, you can get pretty mixed up trying to figure out a black hole.
I tell you, everybody gets mixed up with black holes, and even with PhDs in astrophysics, they get mixed up with them as well. But it's true. So, excuse me. So black holes can have different masses, and that's why we talk about supermassive black holes at the center of galaxies, with billions of times the mass of the sun. But the defining quantity for a black hole is its density, which is either infinite or very near infinite. And so what you've got is all this mass shrunk into a single point, exactly as David said, it's a singularity. And the idea of it tearing space-time it's an interesting one, because I suppose in a way a singularity is exactly that. It's a glitch in space-time because you've got this point of infinite density. But space-time is not destroyed by that, in a way that that a moving black hole would leave a trail of debris behind it. I need to think about that, but as the singularity moves on, space-time recovers, which suggests that there is no damaging effect on space-time of the singularity, unlike the effects that we expect might happen when the universe is expanding so rapidly because of dark energy, and we're now talking tens of billions of years in the future, that you might get this big rip effect where not only does it rip atoms apart, but it rips space-time itself apart. Now, I'm not sufficiently familiar with the physics of that to be able to translate that into what happens with a standard singularity with a black hole. But clearly, it's not having a devastating effect on space-time, or else we'd be in trouble, because there's a supermassive black hole 26,000 light years away from us at the center of our galaxy, which is pretty benign, really. It doesn't do much.
Oh, well, that's good. We don't want it to do much.
No, we don't want it to do anything. There's evidence it has. There's evidence of past gobbling up of material, because we get a light echo from the fact that at a time, if I remember rightly, 70,000 years ago, there was some sort of outburst where the black hole gobbled up something big, and the center of the galaxy became very bright, and we can still see the effect of that on clouds of gas above, or rather below the center of the galaxy, because it's in the southern hemisphere.
Okay.
Something called the Magellanic Stream.
Ah, yes. Yeah. We're still trying to get an image of the black hole at the center of our galaxy, aren't we?
Yeah, that's right. In fact, they may have done it already, and we haven't seen it yet. Yeah. It's very, it's tantalizing.
It is, rather.
That's the Event Horizon Telescope.
That's right. Yeah. So we're pretty keen to see what they come up with. We've already seen an image of a distant black hole that they was obviously in a better position. The problem with ours is all the junk between here and there.
That's partly
which we were talking about earlier.
Yeah, that's right. The stuff, the pollution. The real issue, it was M87's black hole that was imaged, and the real reason for that was that is a much more massive black hole than the one at the center of our galaxy. So it has a bigger event horizon, which is what people were trying to see, the black part of the black hole.
Indeed. All right.
But yeah, it's, I don't know how you detect a trail of ripped space-time either. We certainly detect black holes by the bending effect on space, because we can see this gravitational lensing effect, which we discussed about 4 weeks ago when we talked about intermediate black holes.
Right.
It might have been a bit longer than that. Yeah, intermediate mass black holes.
Okay.
Anyway.
Well, hopefully we adequately answered your question, David, and hope all is well in Texas. Let's move on to someone who's a little bit closer to you and me. Fred, this is Martin. He's in Wollongong, which is just south of Sydney.
It is.
Hi, it's Martin from Wollongong here. In an episode on the 26th of August, you talked about asteroid 2021 PH27. Professor Fred mentioned that it would be subject to relativistic effects. My question is, if we perceive its orbit to be 113 days, and you were to put a clock on the asteroid, would it be less than 113 days? If so, how much less would it be? Is it like seconds or weeks? Thanks.
Wow.
I love that. That's great.
That's a good one. Thank you, Martin. Lovely to hear from you. Relativistic effect, I suppose we better sort of re-educate ourselves on what that means first.
Of course, yeah. So the term relativistic's used when the two theories of relativity become important. And it comes about either because things are moving very quickly and they're affected by Einstein's special theory of relativity. You get time slowing down. You know, if you were whizzing past me at 9/10 of the speed of light, I would see you as being very slow in everything that you were doing. Slower than usual, if I can put it that way. Excuse me. Whereas for you, the time will be passing normally. So that's special relativity. General relativity, however, is what we're talking about here. It's when you're in a gravitational field, then you get time dilation. Time slows down. So yes, our clocks on Earth run slightly slower than they would on even an aircraft. Actually, people have detected this difference. It's in gazillionths of a second. It's tiny fractions, but the gravitational effect is detectable. So on 2021 PH27, which is, if I remember rightly, its nearest is 20 million kilometers from the sun, which is certainly closer than the planet Mercury. The main relativistic effect will be on its orbit, and it will be the same as what Einstein attributed to his theory of relativity with Mercury's orbit. Mercury's orbit has it does something called precession. So it's quite elongated, is Mercury's orbit. And if you think of the long axis of the elongation, that axis moves around the sun. And that's the phenomenon of precession. But it moves in such a way that it can't be accounted for by Newtonian mechanics. If all you know about is the way Newton thought that the universe behaves, which is pretty damn good, it works, except there's a leftover fraction. I can't remember the figures, but you can't account for the precession of Mercury's orbit just by Newtonian dynamics, whereas general relativity explains it perfectly. And it was one of the reasons why Einstein went into ecstasies when he realized that was the case, because people had been trying for 100 years to work out why Mercury's orbit was wonky. And in fact, Leverrier, the great French Italian astrophysicist, he thought there was another planet there, which was never found. He called it Vulcan. Anyway, so that's the main effect on Mercury's orbit, and that will be the same with PH27's orbit. But it's a really good question about, for an observer on PH27, how long is the period? How much does it differ from what we observe? And my guess, and it is no more than a guess, but it's perhaps an educated guess, is that it will be measured in fractions of a second rather than seconds or weeks or days. Yeah, it'll be a very small amount. Yeah. But what an interesting question.
Yes, and Martin, you should be thrilled that Fred compared you to Einstein. So
absolutely, yeah. Well, I'm sure that's right. Anybody listening to Space Nuts must be comparable with Einstein in terms of their patience and forbearance.
Yeah, well, they've got a lot to tolerate with my sense of humor.
They've got a lot to put up. Yeah, that's right.
Oh, dear.
Exactly.
Well, Fred, and thank you again, Martin. Appreciate you getting in touch. Love to hear your voices. So, if you do have questions or comments that you'd like to send us, you can do that via our website, spacenutspodcast.com. And there's the AMA tab up the top. But we also have this access to a thing called SpeakPipe, where you can send us your voice message, and that's on the right-hand side of our homepage. So you can click on that, and if you've got a device with a microphone built in, which most things have these days, you can send us a voice message. Don't forget to tell us who you are, where you're from. We love to know a little bit about you. Maybe describe the weather, I don't mind, or what you're up to. We'd love to know a little bit more about everybody. But yes, we do appreciate your feedback. We've got some text questions we need to get to sooner or later, so we'll be looking at those in the not-too-distant future. We haven't forgotten you. We haven't forgotten you. Well, Fred, that brings us to the end of another program. Thank you so much, sir. It's always good to catch up.
Great pleasure, Andrew. Always good to catch up with you too, and nice to talk to you from the new surroundings.
Yes, indeed. All right, we will catch up with you next week. That's Professor Fred Watson, astronomer at large, part of the team here at Space Nuts. And from me, Andrew Dunkley, thank you for joining us. And a special hello to listeners on the Community Radio Network. This is our first program to go out on the Community Radio Network. So we're thrilled to be a part of that. Hope you enjoy the program. And you're certainly welcome to jump on our website and get in touch as well, spacenutspodcast.com. But until next time, thanks for your company. We'll talk to you again real soon. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
Here we go.